Okay, ready to start?
Hello?
Yeah, ready to start?
What's that sound, teacher?
Christian hymn.
Oh, okay.
Okay, let's make a start.
Yeah. Wait.
Okay.
Yeah, okay. Sure.
Deformation of solid.
Check.
8.1. Yeah.
Just want to ask, that means chapter 6, 7, 9, 10, 11, you will send me all video, right?
Chapter 6 we are done already.
Sorry, 7.
Chapter 7 I sent it to you already.
Okay, then okay. Chapter 8
I
only
record
not
it down
check.
for you. I sent it to you already.
Okay.
So chapter 8, stress and strain. 8.2, force extension graph and stress strain graph. 8.3 is strain energy. Right, as I say, refer to your note. There's your book that we are using. 8.1, stress and strain. Syllabus, define stress and strain for stretch wire or elastic string. Force extension graph and stress strain graph. Sketch the force extension graph and stress extension graph for ductile material. Identify and explain proportional limit, elastic limit, yield point, and tensile strength. Define Young's modulus. Solve problem involving Young's modulus. Distinguish between elastic deformation and plastic deformation. Distinguish the shape of force extension graph for ductile, brittle, and polymeric material. Derive and use a formula for strain energy. Calculate the strain energy for force extension and stress extension graph. Right, that's your topic 7, forces in equilibrium. Right, topic 7, forces in equilibrium. Right, pressure in fluid. And then force can do work. Right, you either move horizontally or you can stretch a string, it will do work. Right, force can stretch or compress a spring. Importance, right? Solid change their shape under the action of forces. This change can be large in the case of spring or hardly noticeable in some structure as building. Right? In wire, in metal, the change is very small. That's why it's called hardly noticeable. Study of deformation of solid is an important aspect of engineering that you require for engineering. This topic provides introduction to both elastic and plastic deformation of materials. Okay, so you need to know, we are more interested in these two cases, A and B, not C. Forces can change the length. Right? In this case, it's tension, where the two forces are moving away from the object, or pulling the object away. So deformation, in this case, we are interested is a change length. In tension, the length of the material increases, like in this case. In compression, like this case, the two forces going in towards the solid, the length decreases. Forces can also cause a change in shape. This is what we are not interested in. Right? So this is compression, this is tension, this is shear. We're not interested in this one, outside the syllabus. Right? So as far as we are concerned, deformation is a change in length or change in shape. Right? There you have a solid metal there. You put a heavy object here on top, then it will bend. Right? These are two support. Sorry, press the wrong button. Okay, so at this part there is compression, where the two arrows are going in, compressing. This part is stretching. So two forces are going out. Right? So this you must be able to distinguish this tension, this compression. Same like the bridges. This part vertical is compression. This part is tension, stretching. Same like this bridge, right? Okay. What do you observe when a material is compressed in terms of length? When it's compressed, what happened to the length? Yeah, there is the original length. You compress it, what happened? What happened to the length? Length becomes shorter or smaller? Shorten? Right? Cross-section area?
Larger.
You have push the material to the side, that's all. The cross-section area becomes larger or widened. K is a poor constant. Now you do in your SPM, K is a spring constant. It depends on the material. And it also depends on length and thickness of the wire used. So it's not good. A constant must only depend on the material, not on the length of material or thickness of material. A good constant depends on material only. So you were introducing the Greek alphabet, sigma, epsilon. Okay, there's the length. Right? We call it tensile stress. Tensile is for tension, stretching. So L is called the original length. And then we apply the force. This one usually is attached to the ceiling. Right? So these are the stress. Right? And then the length becomes, there's an increase in length, delta L. So stress is a normal force. We call it normal because it's always perpendicular to the surface per unit cross-section area, this area, right? Not the side area. The area that's perpendicular to the force. Force divided by area. That's a formula. Force is in Newton. Area is in meter square. So the unit is Pascal, or Newton meter minus 2. Right? Same unit as pressure. Right? Sometimes we use the word tensile to show that it's stretching, tension. And we define another term, tensile strain. Right? We can call this length, L naught for original length without any force, or L. And then we can call the extension, right? That extension as a small x, or E for extension, or delta L. Down the book you use. So we define it as your strain is extension per unit length. All these definition you must memorize one, usually 1 mark. And then write in formula form, extension of the original length. In terms of formula, that's what we want to do. Write in formula form, delta L over L. Delta L is meter, L is meter, so no unit or dimensionless. And finally, Young's modulus, right? Ratio of tensile stress to tensile strain. Right? We like to write in formula form, tensile stress or tensile strain in terms of mass, right? Sigma over epsilon. Sigma is F over A. Right? Memorize this one. No need to memorize the others, but now to derive it. Delta L over L. Right? So we can multiply by L to get rid of this bottom L here. Right? We didn't do anything illegal. So this L and this L cancel off. This L and this L cancel off. So this A can take it down. So we get our FL AL. AL. Just imagine that this is like work. This is not work. Remember, this is not work. Right? This is the original length. But this one is a increase in volume. Increase in volume. Force times original length over increase in volume. Right? Memorize this one. If you can memorize this one, so much better. If not, derive it. Measures the stiffness of the material. Unit is the same. Right? This one no unit. So the same unit as stress, Pascal or Newton meter minus 2. Right? So these are all the equations you need to remember. Okay, these are all the equations you need to remember. Okay, calculate this one. A load of 12 Newton is used to stretch a length of copper wire 1.5 meter long and Young's modulus 1.2 times 10 to the power 11 Pascal. Diameter of copper wire is 1.1 millimeter. Calculate the tensile stress. How to calculate that? What's the answer? Always go back to the formula. The given diameter, given force, that's a force. Right? Have a picture in your mind. If you want to draw original length, that's what is Young's modulus given. So diameter, you can calculate the area by r square. So diameter, change it to meter, divide by 2 to find radius, and square it, and the answer. And go to the formula for stress, F over area, force over area. Force is 12 Newton, that's the area. Calculate that. Tensile strain, right? No extension is given, only original length. So we have to use to go to another way to calculate. Formula, stress over strain. From there we can get our, put our E there, put our stress there, calculate our epsilon. And know that our epsilon is equal to that. Okay, so now we can calculate our extension. Put in our value of epsilon. Delta is what we're going to calculate. L is 1.5. Okay, Ken, you must be able to calculate this simple. Usually is section B. Ken, any comment? Okay, let's carry on. Force extension graph and stress extension graph. There's your Hooke's law. States that extension of a spring, if spring can be elastic material, is directly proportional to applied force, provided the elastic limit is not exceeded. Key is elastic limit is not exceeded. If exceeded, it doesn't follow a straight line anymore. After the elastic limit, the spring does not return to its original length, what we call permanently deformed. Okay, so that's your Hooke's law. Right, know that you are asked, you should be able to write the equation F equals to Kx, and then compare, that's your Hooke's law, compare to the equation of straight line. Equation of straight line, this is your Y, this is your X. So K is a gradient. Right? No need to use gradient, use right? It's called a spring constant or elastic constant or force per unit extension. Right? Find it from the ratio. Right? Force is in Newton, extension is in meter, so it's Newton, meter minus 1. You can go back and show that's also the same as kilogram, S minus 2. Right? That's how we get our unit. Force divided by extension. Force is Newton per meter. Right? In terms of ratio, we just take any value. No need for gradient unless it's experiment. Fastest way is to use choose a value for x1, f1, and calculate your k from here. Right? Take a point on the graph. Right? K is a measure of thickness of the spring, just like Young's modulus. And we can do the experiment. Right? Right? Cram it on end, put a pointer there, add the mass here, and then find the extension. Right? Clamp here so they won't topple over. That's a meter rule. Okay, that's your stress strain graph. How to learn from the graph. That's your stress. Okay, you can take a value. That's your strain. That's your stress. So if we define our stress divided by strain as Young's modulus. So we can see from here, the definition can be rewrite. Take this one across there, or straight away we know it's gradient already. Compare equation of straight line. E is a gradient. Right? It's a gradient or just a ratio of stress over strain. Right? Don't need to memorize this, just know the magnitude. Right? So that when you do calculation, you know the value is between 10 to the power 9 to 10 to the power 12. Usually it's metal. So it's about 10 to the power 11 or 10 to the power 12. Okay. Copper, all that. Relationship between E and K. Right? Go back to our derivation just now. Force times original length, cross-sectional area, extension. And then go to our definition for K, F divided by extension. Then group it up. This one is your K. You get our answer. Right? So K becomes your E. Take the A across, take the L down, cross multiply. That's all we get. Right? So we can see from here, K depends on the material, depends on cross-sectional area, depends on length. That's what we say originally. So it's not a good constant. Problem of determining Young's modulus. Right? You want to find that extension. And E is very large, this is very large. Okay, so what do? We make this one as long as possible. So this one will be as large as possible. Right? And then you want this area as small as possible. So that this one also as large as possible. So we make it thin. Right? Since the extension is likely to be very small, we cannot use meter rule to measure. You have to use vernier caliper or better still micrometer method of measuring. Right? So we usually use a cross-sectional area, very small or thin wire, and measure using micrometer. Right? The diameter we can measure by micrometer. So the wire is long as possible, about 2 meters. It is thin as possible. Right? So that the extension is as large as possible. So we use 5 Newton, the extension is about 1 millimeter. Right? So these are the various apparatus. This one use micrometer method. Your exam you can just use this one, simple. We got 2 wires. One is a control wire, one is a test wire. Right? 2 identical wires, that means they are the same material attached to a fixed support. There's a fixed support. Right? The ceiling, each carrying a mass. The mass is to stretch the wire only. Right? So the control wire is called the reference wire. It carry the main scale. And carry the main scale. There's the main scale, this one. While the test wire, this is a test wire, carry the vernier scale. Right? Vernier scale is to measure the extension. So we put a small mass there to make sure that this wire is straight. A little bit of tension. Then we change the mass here to find the extension. Right? So before we start, we measure this length first, original length. Then we add the mass and note the extension. And repeat, different mass, different extension. Right? And then if we want to find the mass more accurately, we can use a top band balance to measure the mass. And then use a weight formula to calculate the weight or the force on this test wire. right? But precautions, you have to make sure that we don't have this skin, right? That means the wire must be straightened, not twisted. Right? This twisted, when you add the mesh, it becomes straight. So if we add the length to you, so that's why we cannot have that. Taut, we want it to have a bit of tension, straight. Don't want it curved like that. Right? Make sure there's no pins. Otherwise, it will have a big extension when we put a large mesh. Right? So it will give us wrong answer. Then we have to make sure that the elastic limit is not exceeded. Right? How to make sure? Every time we add a load, we remove the load. Right? Remove the load means unloading. Add the weight or loading. Right? And then it should go back to the original length, the original value. If not, that means it has exceeded the elastic limit. Okay, then we can draw the graph, extension against load. Right? Gradient, you can find from the straight line. A divided by B. Right? Equation of straight line, you should be able to draw y equals mx. Y is our x. X is our f. So that one equation. Then we can rewrite our equation for E. It's our equation for E in terms of x first, take our x up, take our E down, take our f to the other side. Okay, let's rewrite the equation of this in this form. That's all. Then we can compare. Right? Gradient is equal to this one. F is a variable, x. So this becomes a gradient, right? Which we can measure from the graph. And from there we can calculate our E, take our E down, take our gradient down. So that's our gradient M. Okay, that's how we do experiment. Ductile material. Right? A ductile substance lengthen considerably and undergo plastic deformation until they break. Such material can be stretched into a wire. In ductile material, initially the extension is proportional to the force applied, then at large extension or small change in force. Right? When the force is removed, it must return to original length. Example of this will be lead, copper, wrought iron, steel. Right? These are some of the examples. So, force extension graph for copper. Example, copper ductile material is first a straight line. Right? Stretch to P. OP is a straight line. That means this region, the way Hooke's law. And then P is called the limit of proportionality. Means it's a straight line passing through origin. And after that, the graph is a slight curve there. Right? That's called the elastic limit. Just around there. Doesn't have to be particular, around there. And then this one where it breaks is called B. Right? E is called the elastic limit. That means up to E, if the load is removed, the material returns to its original length. Right? Except that it's not a straight line. That means this part there, the force is not proportional to the extension. Right? Keep that in mind. But it still returns to its original length. Right? So we are asked to define what is elastic limit. Is the point beyond which the force does not return to its original, the material does not return to the original length when the load is removed. Right? It's just a point on the wire. We can do experiment to find it. After E, slightly after E is your Y. I don't have to worry exactly where, just after E. Right? Don't be too far away, just slightly after E. You point. Loading means you add load. So we usually show a Y arrow there. That's where we add the load. Unloading means we remove the load. right? B is called the fracture point or breaking stress, where the material break. And this region until E, this region there, any extension, any amount of this extension or that force there is called elastic deformation. That means when you remove the load, you return to original length. So all this extension or deformation is called elastic deformation. After that, until it breaks, is called your plastic deformation. So in elastic deformation, when the force on the material is removed, the material returns to original length. Memorize that. In plastic deformation, when the force is removed, the material does not return to original length. That's the difference. Not return. After you exceed that elastic limit, that region is called plastic deformation. Don't be too particular about the shape, but roughly there's a straight line, and after that there's a curve there. Right? And after E is a yield point. That's all. So if the material is stretched to X, right, the point there, then how to draw the graph after you remove the load? Right? You will follow this line, which is almost parallel to this line. So we put an arrow there to show that we are unloading it, we are removing the load each step of the way. So it will come to S. Right? So it's permanently stretched already. No more return to original length. So X is almost parallel to OP. That's to remember. Tensile strength, we define as maximum load that material can support without fracture. Right? So usually it's just maximum load here. Sometimes it can be this point if it's up there. Right? So it's maximum load without fracture when being stretched, divided by the cross-sectional area. Right? So tensile strength is the maximum stress, if you like. Maximum load divided by cross-sectional area. Okay, so sometimes the graph may be here. So that is your maximum load. This is also maximum load. If the graph is this one, same thing, maximum load is there. Or sometimes can be here, depending on which is the largest value. So memorize what is tensile strength. Right? So far we have gone to ductile material, brittle material, ceramic. Force extension graph is that way, a straight line. Remember, you can call it force extension graph or you can call it stress strain graph, same thing, same shape, right? Only value, magnitude different, that's all, but we are not interested in magnitude here. Richter means break after the elastic limit exceeded, but extension is proportional to force until it breaks. Right? Always a straight line, and then this is the elastic limit. That means the material will return to its original length when the force applied is removed. Right? So example of this material will be your chalk or ceramic. Right? Materials such as glass that can be extended but not show the plastic deformation and will only easily fracture. It's called brittle material. So it doesn't have this section there. Right? It's just a straight line. After that, it just breaks. Right? It doesn't have this section. This is called the plastic region. Don't have that plastic region. What's the difference? You can see in real life what's the two different. Right? Brittle, you drop it, it shatter, or you hit it with a hammer, it will break into pieces there. Whereas this one, you hit it, it becomes dented, that's all. Or you drop it, it hits the ground, it becomes dented like a car. Right? Somebody knocked into a car, it becomes dented. Right? But you can glue it back. It looks like original, except a bit ugly with the lines there, that's all. Right? Whereas the kettle, the dent is always there. You drop it, it gets dented. It's always there. Even though you can straighten it like your car. Right? Somebody dented the car, it's permanent. But you can still put it up, but if you look carefully, it's still dented. Right? Rubber, this is called polymeric material. Right? This part is where you apply the load. This part is where we remove the load. Right? The two curve doesn't coincide. Why? Right? Material stretches easily for relatively small force. Right? What happens when you apply a force? The bonds between the chain, which are broken when the material is loaded. Right? You can think of the inside there, the molecules are long chains, and between the change of molecule, there are intermolecular force or the bond. So the bond is broken when you stretch it. So when you break it, this requires work to be done. So more energy has to be put in. That's the reason why. When you break the bond, you need energy. So we call this where the two curve doesn't coincide, we call it hysteresis. Right? The curve for loading and unloading doesn't coincide. So when the load is removed, this is the one where the load is removed. Right? Rubber does not return to its original length. Right? Sometimes some book will show you go to original length, but sometimes it doesn't. But anyway, you will find it warmer. Right? Touch rubber is warmer because some work is done in the material. Right? So summarize, brittle is this one. A lot of force required to take small extension. Ductile is this one. There's a small area there. Polymeric, the rubber band, easy to stretch, small force plus extension. Right? You need to memorize. It can be force, extension graph, or the same. You can call it stress, strain graph. Right? The shape is the same, magnitude only different as well. Okay, strain energy. What is strain energy or elastic potential energy? Ability to do work as a result of change of shape of an object. Right? Same, force extension graph, energy stored in wire is called the potential energy stored in the spring or wire. Work done in stretching the spring, force and distance movement in the direction of the force as our definition. Right? So it's the shaded area, the shaded area is half F times X. Right? Or you can integrate it, right? And replace the force with the spring formula, Kx, it becomes Kx squared. Right? Potential energy stored in spring, sometimes different book will call it differently. Strain energy stored, elastic potential energy. Okay, any comments so far? Okay, so when we calculate the average force times the extension. Average force times extension. Right? So it's area of triangle. Or another way of calculate average force is to make sure that this area of this triangle is the same as area of this rectangle. Right? That's where we get our half F. Okay, that's where we get our average force and half F. Right? F is the maximum force. Okay, that's just to illustrate how to calculate the average force. That's why we have half Fx. Right? Work is done on the bowl. Right? You want to send an arrow out. Work done is stored in the bowl and the string as elastic potential energy. So when you release it, the arrow said to have potential kinetic energy. Okay, so conservation energy, loss in potential, elastic potential equals to gain in kinetic energy. Right? You can rewrite that. Stress strain graph, same thing. Right? Area of this triangle, if that's your strain, this is your stress. You get area of triangle is half sigma epsilon. Right? Or sigma is F over A. Epsilon is your extension of the original length. Okay, so this one is work done. F times delta L is work done. That one is your volume of the material. Right? AL is the volume of material. So we can call it work done per unit volume. Okay. Derive it or memorize it. That's the formula, alternative formula, either delta L or X. Or we can call it energy stored per unit volume. Okay, so far? Stop me if I'm going too fast. Right? So how to interpret? Okay, arrow show loading, you add the weight, you have the load. So after this, E is the elastic limit, S is just any point after that. And this is the area X. X is the work done in elastic deformation. Remember, E is the elastic limit. So this is the area for elastic deformation. Then we have our Z. So area X plus area Y plus area Z is the work done in loading. We load up to S. Okay, that's your area Z. That's your area Y. Right? We show it unloading. We show an arrow down there. This is unloading. We stretch up to S and unloading. Remove the load. So Z is the energy that's recovered. Right? Whatever energy we put in, we get it back. So the energy recover. Right? We need to know how to interpret. That's returned to us. X and Y doesn't return to us anymore. Right? Area X and Y, energy converted to heat. That means it has done work on the molecules of the material inside there. How do we know? We touch the object like rubber, you feel warm. So that's energy converted to heat during unloading or net work done. Right? X and Y, area X and Y is the net work done. Okay, so net work done convert to heat. That's why we touch the object rubber. When we stretch it, it becomes warm. Right? Because something internal has changed in the molecule there. Okay. All these formulas you need to remember. Right? Series and that one is your STPM work. I don't think they will come out. Right? Tensile strength, remember. Stress, remember the definition. Strain, remember the definition. Young's modulus, remember the definition. Right? Stress strain graph. Does it represent area is the energy stored per unit volume. Gradient is Young's modulus. Right? Deformation is force on different material. Force on different material. Well, it can be stress, can be strain, doesn't matter. The shape look the same. Brittle, this one. This one is your ductile. And then this is polymerate. Sometimes can go this way or sometimes go the other way, doesn't matter. As long as you know how to distinguish them. Okay, let's try partial paper. What's the answer for this one? Which property or material is not due to plastic deformation? Yep, what's the answer?
Plastic deformation. Boy.
No, plastic deformation ductile material is A.
Okay.
It cannot bend.
Not
It
C,
will
man.
break. I don't know why your answer gives C. The book gives C. It should be A because brittle cannot bend. Right? Brittle material breaks soon after the elastic limit is exceeded. So it's hard to bend a brittle material. Ductile, you can bend it. You can stretch it beyond the elastic limit. Thus, you have your plastic deformation. Ability to bend is a property of ductile material. Ability to withstand stress is for all material, not only for brittle material. Okay, what's the answer for this one? Variation of
This one?
stress. Say again.
No. This one. Boy. The answer is boy.
Variation of stress strain graph for P and Q until breaking. Right? There's your breaking point here. There's a breaking point here. Shown in the graph, which is true about P and Q. Q
Boy.
steeper than P, wrong. Right? Gradient, this one is bigger. Bigger means steeper. Right? So A is false. P is ductile, wrong. P is brittle. Q is ductile. You should be able to recognize, false. Q is more difficult to break compared to P. Yeah. Well, it doesn't break here. It still break at the end there. True. It take a longer time. This one break very fast. No other area really. After the elastic limit, it break. And material P needs more work. Smaller area. Area in the graph is energy stored per unit volume or work done per unit volume. This one is larger. Before it break, there's a larger area. Okay, so answer is C. Okay, the stress strain graph of different material P and Q are shown below. Each material fracture at point P and N. Which statement is not true about the properties of P and Q? Yep. Yep. Yep, what's the answer? Why take so long? Q has a lower elastic tensile strain. Tensile strain is look at the stress as well. Maximum stress. Right? Maximum stress, so wrong. That's your maximum load over cross-section area. So in this case, it's the maximum stress as well. So A is true. Q has a lower tensile strain, lower, so larger. P has a greater proportional limit. True. Greater stress, greater proportional limit. P has a greater value of Young's modulus. True. You will get from the gradient, greater slope. Q has a greater energy store, right? For a particular strain. Q has a greater energy, no? Right? Area under the graph is smaller than P, so false. Right? Area under the graph is energy stored per unit volume, so Q is smaller for a particular strain. Okay. The answer is donkey. Okay, what's the answer for number 4? The stress strain graph for 4 different material PQRS of the same dimension are shown in the graph below. That means same area, same length. Which statement is not true about the curve? Right? You want not true. Yeah? All this must be in your head already. P is the strongest. True. Right? Strongest, greater stress here, the largest among all the others. Q is more brittle, right? Q is brittle, correct? Right? Doesn't have the elastic limit. This is a brittle material, Q. R is most ductile, yeah. There is the elastic limit somewhere here. It can stretch a long way before it breaks. So true. S is the steepest. Steepest, remember, the gradient gives Young's modulus, so it has the smallest Young's modulus. So no, right? Cannot be the steepest. So that's the false one. Okay with that? Yeah, still not ready yet. Go back and revise. Okay, let's carry on. Since our time is running out. What's the answer for this one? Wire of 5 meter and cross-section area given is stretched to an extension of 1.84 millimeter. If the stress on the exerted on the wire is given, what is the strain energy which is stored in the wire? Right? We want to calculate work done or energy stored. Remember to change it to meter. Yep, what's the answer? Right, calculate your force first. Half Fx. So calculate your force from the stress formula. Force over area. Area is pi r by d square. Oh, sorry, pi r square. Right, I put 4 there lah, but you can use r if you want to. D divided by 2. Then you will get 4 there. Right, so it's sigma cross multiply. Want to find force. So that is that's your stress. That's your stress. That's your area given. Take the area across there. That's the area given. Calculate that, get your force. And use the formula for half Fx. Half. That's your force. X, the extension. Right, this one, change it to SI unit. Right, so answer is B. Can you go back and review? Whatever you've forgotten, you go back and review. Trying to push it as much as possible into you. Right? Not regular. Not every year will come out. Okay. The variation of stress strain graph. Right? This is 2019 U. The variation of stress strain graph for two different material X and Y until breaking point of the material is shown graph below. Based on the graph, state two differences in property of X and Y. Give your reason. Yeah? Two different properties of X and Y. Can? X is brittle. Right? No ductile, no plastic deformation, no this curve there. After that, it breaks. Y, you must know, is ductile. So how do you know what is the reason? Reason because X break as soon as the elastic limit is exceeded, while Y has a plastic deformation. That means it got this region. Right? Greater gradient. So X is steeper than Y. X has a higher Young's modulus. Right? If you want, you can state that Young's modulus is obtained from the gradient. Okay, that's how you're supposed to fill up for your answer. Determine Young's modulus for X. Right? This is your section B. Memorize formula. And read from graph. Right? They're giving you the value. Right? As long as the right unit, correct. Divide, no need to change the unit, then get the answer. Determine the required tensile force to break Y. If the cross-section area is given, so they are very kind to you, they read for you, right? The value. Tensile stress, right? Or tensile force. Tensile force divided by area. So tensile stress is given. Read that, the value there. Remember that value there, 10 to the power 7. So tensile force, take across area, the stress, right? 20 times 10 to the power 7. Area is given. Calculate out 157 Newton. Okay, section B is usually very straightforward. Section C is more application, more tricky a bit.
Okay, section C mode application.
Right, you can apply different region or syllabus. Right, you can see it's not regular. Section C, not regular. Right, let's try one question. The formula for V of longitudinal wave which travel along the rod, material Young's modulus E, density that is given by that. Right? This is your third term work, right? Doesn't matter. They tell you what it is. You need to know the definition and apply. That's all. Show that the formula is dimensionally correct. Right? You just show the unit on the left hand side and unit on the right hand side is the same, or dimension. The dimension of V is LT minus 1. Right? E, go to the formula. Right? Dimension of E, F is MLT minus 2. L is L. Area is L square times X. This is volume. So it's L cube. So MT minus 2. That one L square. So you still got L minus 1. Then you want this dimension for this one. Right? So dimension for this one is just a square root. This is your E. And then there's your density. M and N can cancel off. L you take to the top there is you got L square. L square square root, it becomes L. Then square root of this one becomes T minus 1. So they have the same, right? Same dimension. That's all. That's what we are supposed to show. Sketch the graph of tensile force against extension for copper wire until it breaks. Mark the U point on the graph. That's all. Right? And then change this stress to force, that's all. This one change to extension. Right? It's the same, whether it's stress strain or it's force extension. Right? That's your U point. Okay with that? Change that to force. Change that to extension. Okay? The U point is that point there. Slightly more, slightly doesn't matter. They just want to know, you know where to roughly it is. Right? You can see that this is chapter 7. The chapter 8 are together combined. A uniform wire of length. Right? That's the original length, AB. Connected to fixed point A and B. At a horizontal distance, 2.4 meter apart, as shown in the diagram. Then you add the load as the wire now. A mass of 2 kilograms, that's your mass, 2 kilograms, is hung at a midpoint C, that's your midpoint C. Neglect the weight of the wire. You don't want to worry about the mass of the wire at all. And then you are told the Young's modulus. Calculate the strain of the wire. Right? So to calculate the strain, you must calculate this length first. Right? This length first. So you are given this height. The whole length is 2.4. So this is midpoint. So this is 1.2. Right? So from there, you can use your trigonometry to calculate your AC. Right? AC is 1.2 square plus 0.7 square. Square root that is 1.23. Then find the extension. Extension is 1.23. Right? This length there minus this length. This is the original length. 0.03. And then right, strain is extension, that one, divided by original length. Original length is 1.2. Calculate the stress on the wire. Right? Stress. They didn't give you area, so you cannot calculate that. So you go to the other formula, strain over E, strain times E. Right? Strain is given. E is given. Right? That's your E. Calculate out. Calculate the energy stored in the wire. Right? Calculate energy stored in the wire. Remember, there are two wires. You can calculate for this part. You have to calculate the tension first. Right? The weight, calculate out mg, 2 times 9.81. That's how we calculate this value. Okay, then you can calculate this angle theta. That depends on how you can different way of solving it. I want to find the angle there. So this angle, I take this triangle. Right? Tangent theta is 1.2 divided by 0.27. Calculate out is 77.3 degree. Then I resolve it vertically. Right? T cos theta, that's why I get 2. Cos theta is 77.3, balanced by 19.62, and calculate my T. Okay, energy store is half kx. Right? For this wire, this side is half tension times x. For this wire, there's another one the same. That's why I multiply by 2. Right? Put in your value, calculate out 1.3234 joule. Yep. Any comments so far? Anything not clear? Right? State the assumption. Right? Remember, we were interested in the straight line path. Sorry, press the wrong button. Okay, wire obey Hooke's law. That's the important thing is the straight line. Proportional limit of the wire is not exceeded. Right? Doesn't exceed. If you exceed, it's no more a straight line. So you cannot apply what we have studied so far. So anything to ask? If not, I will stop here. Anything to ask?
Not yet. Just get out the paper. That's it.
Yeah, have confidence. Review through. Remember all the formula, not the apply. Always.
Oh yeah lah. Now another 200. That means can remember the thing very easily because
You
last
need help,
time
you
means
just
then
ask God to
remember
help you.
means will forget lah.
Yeah, you need help, you just ask God to help you. I will just ask God to help you. I pray for you. Heavenly Father, you
I
help
just want to pass the paper.
as he study, help him to remember what he studied, help him to do well, so that he can be thankful to you. I thank
Won't
you.
be nervous in the
Yes,
paper.
amen. Yeah. If you need help, just ask God to help you. You remember all the formula.
See, thank you so much, teacher.
Okay, so I will stop here.
Thank you, teacher, so much. I hope I can do it, teacher. Hello?
Yeah. So
yeah, hope I can do well, teacher.
Yeah. If you want, when you want to start the class, let me know. All the best to you. God bless you. God help you. I'll pray for you.
Yeah, I'll finish my exam on Thursday. So yeah, maybe the week after that I can start, I guess.
You can take Friday off and then start on Saturday if you want. 1 hour.
Okay. Sure.
Okay. You stop here.
Yeah, no. Oh, teacher, then it'll be some more stressful, teacher.
Say again.
It'll be more stressful.
Take a break off. Take Friday off.
No, because there's 2 semesters to focus. You have